A lattice plane parallel to the x-axis makes the intercept 1 and 1 along y and z-axis. The Miller indices are. Now there are steps to calculate Miller indices. First step 1 is to locate the intercept. Step 1 is to locate the intercept. See, if a plane is parallel, that means its intercept is infinity. If a plane is perpendicular, its intercept is 1. Here in the question they have said a lattice plane parallel to the x-axis. So the intercept for x-axis is infinity because the plane is parallel. Makes the intercepts of 1 and 1 along y and z axis. They have given the intercept of y and z. So the intercept of y is 1 and the intercept of z is 1. So this is the first step. Then comes the second step. The second step is write in terms of lattice constants. Basically we have to do is write these values in the brackets, that is infinity, comma 1, comma 1. Step 3 is to take the reciprocal. We have to take the reciprocal of these above values, that is 1 by infinity, comma 1 by 1, comma 1 by 1. 1 by infinity is 0, comma 1, comma 1. So these are the Miller indices for the intercept infinity, 1 and 1. 0, 1, 1. So the answer is 0, 1, 1. There is also a step 4. Clear fractions if any. If we have any fractions, for example, if we have intercepts x is equals to 2, y is equals to 3 and z is equals to infinity. If we have intercepts 2, 3 and infinity, if we write them in lattice constants, we will get 2, 3, infinity, and the reciprocal would be 1 by 2, 1 by 3, infinity. So here we get the Miller indices in the fraction form. So we have to clear the fractions. Basically what we have to do is take the LCM of these three. Here the LCM is 6 and multiply the LCM with the bracket. So it would be 6 by 2, 6 by 3, 0. Sorry, this is 0. This will be also 0. This 2, 3, 3, 2. So the Miller indices would be 3, 2, 0 for the intercepts 2, 3 and infinity. Okay, these are 4 steps to calculate Miller indices. Next, the diamond structure has a space filling factor that is dash of the closed pack structure. See, the space filling factor is also known as packing efficiency. Packing efficiency is also called space filling factor. In the last video, we saw some values of the packing fraction of simple cubic, BCC and FCC. Here they have asked the actually they have asked the relationship between the diamond structure and the closed pack structure. The closed pack structures are nothing but FCC and HCP. FCC and HCP are known as closed pack structures. In the last video we saw that the packing efficiency of FCC and HCP is same, that is 0.74 or 74%. So we have to remember that the packing fraction for diamond is 0.4 or 34%. They have asked the relationship between the packing fraction of the closed pack structure and the diamond. If you look at the option A, approximately half of the closed pack structure. That means if you look at option A, 0.74, approximately half is 0.74 by 2. So it comes up around 0.37, which is really close to 0.34. That means it is approximately half. The diamond structure has the space filling factor that is approximately half of the closed pack structure. So option A is correct. If you look at option B, approximately 1/3, that means 0.74 divided by 3, it comes up to around 0.24. And if you look at option C, approximately double, that means 0.474 into 2, it comes up to around 1.48. And option D almost the same, it's not possible. So option A is correct. In a cubic crystal, the interplanar spacing HKL planes is represented by DHKL. Which of the following is true? Okay, we know that the interplanar spacing is given by DHKL is equals to A divided by root of H square plus K square plus L square, which means bigger the values of HKL, smaller will be the value of DHKL. If you look at the option, they have given D11, D110, D210 and D100. So if for D11, A is equals to root of 1 square plus 1 square plus 1 square, which will be A by root 3, which comes up to around 0.577A. For D100, A divided by root of 1 square plus 1 square plus 0, which is equals to A by root 2, which comes up to 0.707A. For D210, it comes up to around 0.447A, and for D100, it is A. If you look at the options, D111 is greater than D100. D11 is greater than D100. No, because D100 is greater than D11. So option A is not correct. D110 is greater than D11. D110 is greater than D11. So option B is correct. D11 is less than D20. D11 is less than D20. Option C is also wrong and option D is also wrong. So the correct option is B. KCl crystal has the density of 1.98 into 10 power 3 kg per meter cube and its molecular weight is 74.55 gram. The interatomic distance is, they have given Avogadro number. Let's see. To calculate interatomic distance, we have a formula. Rho is equals to Zm divided by Na into A cube. Rho is density. We have to calculate interatomic distance A. So A cube is equals to Zm divided by rho into Na. Na is Avogadro number. They have given KCl crystal. KCl crystallizes into FCC lattice. Since it is FCC lattice, that means Z value is equals to 4. They have given density, rho is equals to 1.98 into 10 power 3 kg per meter cube. Molecular weight 74.55 gram. If we write this in kg, we will get 0.074 kg. They have given Avogadro number 6.023 into 10 power 23 gram atoms. Substitute these values in this formula. We will get A cube is equals to Z is 4 into 0.074 divided by density 1.98 into 10 power 3 into Avogadro number 6.023 into 10 power 23. If we calculate this, 4 into 0.74 will be 4 into 0.074. 0.296 divided by 1.98 into 6.023. 11.92 into 10 power 23 plus 3, 10 power 26. Then a cube is equals to 0.296 divided by 11.92. 0.024 into 10 power plus 26, it becomes minus 26. Then a is equals to cube root of 0.024 into 10 power minus 26. Cube root of 0.024 into 10 power minus 26. So the answer is a is equals to 6.21 into 10 power minus 10 meter. 6.3 into 10 power minus 10 meter. Next question is also same. An element crystallizes into FCC structure. See, FCC, that means Z is equals to 4. Z is equals to 4. 208 gram of the substance contains 4.28 into 10 power 24 atoms. 208 gram substance contains 4.28 into 10 power 24 atoms. So we have to divide this number by these atoms by Avogadro number, that is 6.023 into 10 power 24. It comes up to around 7.1 gram per mole. If we write this in kg, we will get 0.071 kg per mole. And then this value we have to divide it by 0.071 divided by, this is also in gram, 208 gram. If we write this in kg, we will get 0.208 kg. It is 0.208. Okay, this value comes up to 0.00. If we convert this into kg, it is 0.0071. 0.0071 divided by 0.28. 0.0071 divided by 0.208, it is 0.034. This is molecular weight, and they have given density. Density rho is equals to 7200 kg per meter cube. Same formula, a cube is equals to Zm divided by Na into rho, which is equals to, Z value is 4 into 0.034 divided by Avogadro number 6.023 into 10 power 23 into density rho 7200. A cube is equals to 4 into 0.034. 0.136 divided by 6.023 into 7200. 43365.6 into 10 power plus 23, that means it is minus 23. A cube is equals to 0.136 divided by 43365.6. It is 3.136 into 10 power minus 6 into 10 power minus 23. Minus 23 minus 6 is minus 29. So a cube is equals to 3.136 into 10 power minus 29. A is equals to cube root of 3.136 into 10 power minus 29. So A is equals to cube root of 3.136 into 10 power minus 29. The answer is 3.1 into 10 power minus 10, or A is equals to 3 angstrom. A is equals to 3 angstrom. A simple cubic crystal, X-rays of the wavelength lambda alpha is different from that of 100 plane at a certain angle theta, and of the wavelength lambda beta from the 110 plane at the same angle. The ratio of lambda alpha by lambda beta. This is the question of Bragg's law. We know the formula for Bragg's law. 2d sine theta is equals to n lambda. Interplanar spacing for 100 plane 1 divided by root of 1 square plus 0 square plus 0 square, which is nothing but 1 by root 1. And for 110 plane 1 divided by root of 1 square plus 1 square plus 0 square, which is equals to 1 by root 2. So they have asked the ratio of lambda alpha by lambda beta. D1, if we put all these values as constant, that means D is directly proportional to lambda. D100 divided by D10 is equals to lambda alpha by lambda beta, which is nothing but 1 by root 1 divided by 1 by root 2, which is nothing but lambda alpha by lambda beta. That is 1 by root 1 into root 2 by 1 equals to lambda alpha by lambda beta. So lambda alpha by lambda beta is equals to root 2. Option C is correct. X-rays of the unknown wavelength are diffracted from an iron sample. First peak is observed for 110 plane at 2 theta equals to 44.70. If the lattice parameter of BCC iron is 2.87 angstrom, then the wavelength of the X-rays used is. This is also a Bragg's law question. 2d sine theta is equals to n lambda. They have given the planes for D110. For D110, the value is a by root 2. A by root 2. They have given the lattice parameter A. A is equals to 2.87 angstrom. So D value will be 2.87 divided by root 2 angstrom, which is equals to 2.02 angstrom. We have got D value and they have given 2 theta value. 2 theta is equals to 44.70, then theta is equals to 44.70 divided by 2, which is 22.35. Therefore theta is equals to 22.35 degree. What they have asked the wavelength lambda. So 2d sine theta is equals to n lambda. 2 into d is 2.02 into sine theta is 22.35. Lambda is equals to n is equals to 1 first, because first order diffraction. It is a first order diffraction. 2 into 2.02 into sine 22.35. Answer is 1.53 angstrom. That is 1.5 angstrom. Option C. Next, in case of instability in a cubic crystal, for a cubic crystal, this is important. For a cubic crystal, the bond stability criteria are There are criteria for the cubic crystal stability. The first criteria is C11 minus C12 should be greater than 0. The second criteria is C11 plus 2C12 should be greater than 0. And the third criteria is C44 should be greater than 0. We have to remember this. These are standard values. So if we look at the options, C44 is less than 0, but C44 should be greater than 0. C44 is greater than 0. This is correct. C11 is greater than C12 is wrong. C11 is equals to C12. So we can say that this is also correct because C11 is greater than or equals to C12. We can say that, but I am not sure about this option, but option B is correct. In a divalent metal with BCC lattice, the lattice constant is 2 Armstrong. The electron density is given by. The formula for electron density is given by N is equals to Z into N. N is nothing but atoms per unit cell divided by A cube. This is the formula for electron density. They have mentioned divalent metal. Divalent metal, that means number of atoms per unit cell is 2. With BCC lattice, BCC lattice means Z is equals to 2, and they have given lattice constant as 2 Armstrong. E is equals to 2 Armstrong. So the electron density will be 2 into 2 divided by 2 into 10 power minus 10 whole cube, which is nothing but 4 by 2 cube is 8 into 10 power minus 30, which is 1 by 2 into 10 power plus 30 per meter cube. Here in the options they have the answers are in centimeter cube, per centimeter cube. That means we have to divide this by 10 square into 3 cube because it is in centimeter cube. Then N is equals to 1 by 2 into 10 power 30 divided by 10 power 3 to the 6, which is nothing but 1 by 2 into 10 power minus 10 power 30 minus 6, which is nothing but 1 by 2 into 10 power 24. So the option is 1 by 2 into 10 power 24 centimeter cube per centimeter cube. Also for this question, remember the values of the packing fractions. The packing fraction for diamond, as I said, it is 0.34. Zinc blende or ZNS, it also has the same packing fraction as 0.34. Cesium chloride, CHLORIDE, cesium chloride has the packing fraction of 0.68, which is similar to BCC structure. And sodium chloride, NaCl, it has the packing fraction of 0.74, which is similar to the packing fraction of FCC and HCP. Remember these values. Rest questions I will solve in the next video. Thank you.